Previously we saw how to create a frequency curve, how the frequency curve came about. Because as the number of bars in the histogram increases, the polygon has more and more sides, starts to look smooth, so you call it a curve. What we want to look at are the types of frequency curve. Now you have the U shape, the skew to the right, skew to the left, reverse J shape, and the normal curve. Now the normal curve is the most common, it's very important, and we'll give it special treatment in a different video. Now the U-shaped curve, let us say this is our vertical and horizontal axis, and we want a U-shaped curve. The U-shaped curve, oh no, this sometimes happens with the software. The U-shaped curve will look something like this, right? Like a U. Now, a certain situation might give rise to it. For example, suppose this is, let me see now, 8 a.m. This is 12 noon. This is 5 p.m. This could be the traffic, how heavy the traffic is throughout the day. A lot of people are going to work at 8, between 7:30 8, heavy traffic. The traffic goes down by midday, you know, there isn't much traffic. But then later on, the traffic builds up again as people are coming from work and school, right? That could give a U-shaped curve. This could also be the sales of newspapers. Roadside vendors selling newspaper, the total number of newspapers sold, right? At the traffic lights, you have a lot of persons buying the newspapers because a lot of traffic is on the road, persons going to school and work. And also in the evening as they come from school and work, they're buying the evening newspaper. But in the middle of the day, you don't really have as much sales because there isn't a lot of people traveling or backed up at the traffic lights. Alright, so that's a U-shaped curve. You have another one, the skew to the right. Now the skew to the right, some of them, or generally, it might look somewhat like this. Alright? And I could exaggerate it a bit. Make it more exaggerated. I go up high, go down low, like this. Alright. Now, you might say, how is it that this bump is on the left and yet it's called skew to the right? The thing is, this is really, this curve is skewed to the right. The side that you mention is really where the long tail is. You're looking at the tail. This is a tail. Alright? It's like a dog. The dog's head is here and the tail all the way out here. So the dog turns so that its tail is to the right. So it's skewed to the right. Sometimes it's called a positively skewed distribution or curve. The curve shows a distribution, so I'll also say distribution. So the skew to the right is also referred to as a positively skewed distribution. Now, you have certain situations that can give rise to it. Suppose, for example, This is number of households, right? Number of households. Let me correct that. So you have persons living at home as families. This could be number of children on the horizontal, number of children in the families. So you have a few families with no children. You have a larger number of families with one child, and the largest number of families, this could go up to say 1,500, 750, 250. Right, just putting some numbers here. So you have say 50 families with no children. You have about 100 families with one child. 2 children goes all the way up to 1,000 families with 2 children. Then at 3, you don't have as many. You have, call it about 750 families with 3 children. At 4 children, you have only 200 and something. 5. So the thing is, persons are saying that they cannot afford more than a few children. So at the same time, they want to have children, at least 2. So you have some persons haven't had a child yet. A lot more have 1. Many have 2. Then at 3, it starts to go down. 4, 5, and the number drops rapidly. Only few families have 5 or more children. Alright, it could be that. Another situation I'm thinking of is that it could be a large number of persons, a large number of students who got a test. And what you have is a case where you have percentages here. 0, 10 is a very, very hard test, very difficult. And have 10%, 20, 30, 40, 50, 60%. And the test was so hard. Had 1,000 of them, got only 20%. Few got less than 20, maybe 10, 250 of them got 10%. 700 and odd got 30. But only few of them actually got over 50. So you can say it's skewed to the right. Maybe when they were setting the test, they were thinking of those who were able to do very well in the test, and they would appear to the right of this curve. 70, 80, 90, 100. Very, very few persons got 80%, 90, 70. Because of how hard the test was, the bulk of persons got less than 30%. It could be that. So it's skewed to the right. Alright? Who got the marks to the right were those persons who the test designer was considering, and say only those that they want to pass. They don't want a lot of persons to pass. Alright, so this is a skew to the right. The tail goes to the right. Let's look at the skew to the left now. Skewed to the left. Of course, you have a long tail to the left, right? And it goes way up, and and then down on the right. Let me erase part of this. I want it to look a bit smoother. So it goes way up and then drop down like that. This is a skewed to the left, and it is called a negatively skewed distribution. It's negatively skewed to the left. That's where the long tail is. Now, what could possibly give rise to this? It could be where you have, again, a test. 1,000 persons got, say, 80%. Very easy test. So I've got 90, you have 70, 60, 50, 40. Hardly anybody failed. Alright? The bulk of them passed, and a lot of them got 80%. So when the test designer was putting this test together, they were thinking of those persons who were less able to pass this test. So their marks would have been to the left here. So the thing is, they set it very easy, and it was so easy. The bulk of persons, 1,000 of them, got 80%. You had maybe 200 and something of them got 90, 60, about the same, 50, and about 120 persons. But very few persons fail. Right? The bulk of persons actually pass. So it could be a case like that. Right? It could be a case like that. Now, another situation I'm thinking of that it could represent is where, for example, there's a deadline to pay or to file your taxes or to pay a fee to renew your ID, something like that. Now, it is due on this date. So this date is on Monday the 5th of the month. You have a few persons coming in from the previous week, from the previous Monday, Tuesday, Wednesday, Thursday, Friday. It's open on Saturday and Sundays too. Persons coming in, and as it reaches closer to the deadline, you have a lot more persons coming in. But then on the deadline, persons were, what they say, procrastinating. They were putting it off, finding other things to do. But then they saw that the deadline had come and everybody panicked, and you had this big crowd, a lot of people trying to get through on the deadline. So the number of persons was very large on the deadline. Some persons didn't get through. Some persons said the lines were too long. The crowd, there was too much persons. They couldn't wait, and they would be charged a late penalty after Monday. So on Tuesday, persons coming in, paying the late penalty and paying their fee or registering, whatever the case may be. So that could be a case. It could be a case like that. Alright? So that is the skewed to the left, or the negatively skewed curve. Now, let's look at the other curve. Let me get rid of this. Now, the reverse J-shaped curve. Let me use a thicker line. It could be a situation like this. That's the reverse J shape. Let me draw that again. The reverse J shape curve. Now you might say the letter J looks like this and it's shaped like a J, so why did they call it a reverse J shape? Well, I guess the J that they're talking about might be one that is turned sideways, right, like that. But in any case, the reverse J shape is this one, and let me label it. Where is it? Reverse J shape. This one, right? That's the reverse J shape. This could be a population growth. Could represent population growth, whether it's human population, bacteria, or whatever it is. Right? You have an increasing number as time goes by. For example, if you have bacteria, you're in biology, and you have bacteria growing in a jar, and you're checking every hour. Say you start the bacteria, measuring the bacteria growth stage at 8 o'clock, and at 9 you have an increase, at 10, 11 o'clock, 12 o'clock. So you have a rapid increase in the growth of bacteria. It could be that. Alright? So that's one way, that's one example of where you have the reverse J-shaped curve, or the reverse J-shaped distribution. Now let's look at the J-shaped distribution. Well, of course, the J-shaped distribution could be, let me use a thicker line and black. It could be a case like this, you know, going down like that. In this case, you have decay. The previous one was growth, and this one is decay. So this is what? J-shape. Alright? This is a J-shaped curve. Now, you could get this curve if, for example, you have a pot of boiling water and you have a thermometer and a clock. Water boils at 100. Those in science, water boils at 100. 50. Let's say the room temperature is 30. Here, you just turn off the stove and you measure at, it could be, say, 9 o'clock. You measure the temperature at 9 o'clock. Why my 9 looks like this? I want to erase this 9. Alright, that's the 9. Let's say at 9 o'clock. Then you measure the temperature again at 9:30, 10 o'clock, 10:30, 11 o'clock, and so on, and you plot a graph. What was the temperature at 9:30? What was the temperature at 10 o'clock? Temperature at 10:30? You could measure it every 15 minutes, every 5 minutes, whatever the case may be. Alright? But the idea is that the pot, the water will cool. It will cool down rapidly at first, then more slowly. So when you draw a curve through these points, then what you have is this curve that is called the J-shaped curve. You see that? Now, that was a J shape. As for the normal curve, We're going to talk some more about it later on, as I said before. But the normal curve, let me try my best. It is symmetrical. Like this. Alright. Now, by symmetrical, I mean if you take a mirror line and draw through the middle, if you fold the left and fold the right, you draw it on a paper, you fold it right on this mirror line, the left and right would match each other. That's a normal curve. That is called the bell curve, because the bell, the shape of the bell is somewhat like this. You have the bell, and then you have the part that hits the side of the bell, and you have the angle that you hold. Alright? Now, that it's the bell-shaped curve, and it's a normal curve. Now, you get that curve generally when you study a large number of items, large number of people, whatever the case may be. So this is called the normal curve, or the bell curve. So those are some of the most common types of frequency curve. As I said, later on we'll talk, in a different video we'll talk some more about the bell curve. I will see you then.